So it turns out that our clock actually doesn't arrive at all registers at the same time. And that is because, well, it's physically impossible, right? We have a few registers and they're separated in space. And in fact, if you have a big chip, there may be registers that are, clear up here and registers that are clear down here. And if our clock were coming in here at this point in our chip, now there's a long delay for our clock. And so this difference in the clock edges, right? We get a clock edge here, and only sometime later does this register see the clock edge because of this delay. And so this difference in clock edges is called skew. So here's an example of clock 1 and clock 2, and there's a difference between the edges. The frequency is still the same, right? It's still derived from that same clock, but for example, this clock 2, is earlier than clock 1. We get a clock edge on clock 2, which is earlier, and then some delay later, we get the edge on clock 1. And this can be a varying range, right? So these hash lines here, these lines here, mean that, well, it could vary. The worst case is that it's delayed by, or the difference between those clock edges is T skew. And so when considering skew, we're going to perform a worst case analysis to guarantee that our dynamic discipline is not violated for any registers. There are many registers in the system, so we're going to find the largest delay, make it work for that, and then maybe some other, the clock between some other registers are here and here, so a little bit less, but we're going to consider that the worst case possibility between two edges, which is the worst case. If it works for the worst case, it's going to work for those kind of intermediate worst cases or intermediate bad cases as well, or delayed cases. So let's talk about the setup time constraint or the cycle time constraint in terms of when we have to consider skew. So in the worst case, clock 2 is earlier than clock 1. So I'm going to redraw the waveforms for the clocks here. So here's clock 1 into register 1. And clock 2 is earlier than clock 1. So they still have the same frequency, but clock 2 is earlier, so clock 1's edge is delayed with respect to clock 2. And so we still have this, this cycle time, TC is still this entire time from here, from edge to edge of a given clock. Right, that cycle time, we still have that cycle time for clock 2 as well. Same cycle time, just delayed edges. And so let's see what happens. Well, our data is going to be clocked into the circuit with clock 1. After that clock edge, it will come out of register 1. The latest time would be TPCQ. It's going to go through our combinational logic, TPD, and then we need to have it set up and get into register 2 by clock 2's edge. So clock 2 is the one that is sampling D2, and so that has to set up before clock 2's edge. It has to be stable and available in that internal node of R2, of register 2. And so instead of having this entire cycle time to do that work, we actually have a cycle time minus, well, what's this difference here? The difference between these two edges is the skew. So instead of having a cycle time to do all of that work, we actually only have a cycle time minus T skew to do that work. So TC minus T skew has to be greater than or equal to, well, all that stuff that we need to do. Propagation clock to Q, get it out of the register, plus get through the combinational logic and set up into the next register. And so that stuff we need to do is the same, but now we just have less time to do it. We don't have the entire cycle time. We have a cycle time minus T-skew. And we can bring T-skew over to the other side, plus T-skew, and we have an equation then for Tc greater than or equal to all of this work we need to do plus T-skew. And so looking at these pre-drawn figures, we clock in our data from clock 1, TP-CQ later, plus TPD plus a setup time is the stuff we need to do. We have to do that before the next clock edge. Well, the next clock edge is being driven by clock 2, right? The clock that's clocking out the data at D2. So instead of having TC, this entire cycle time to do the work, we only have TC minus, well, the difference in these edges, so minus T-skew. And we can bring skew over to the other side, and we get TC is greater than or equal to TP-CQ plus TPD plus T setup plus T-skew. We basically increased our cycle time by that skew amount. And remember that the frequency of the clock is equal to 1 over the cycle time. So for example, if we have a cycle time of 1 nanosecond, 1 over 1 nanosecond equals 1 gigahertz. As we increase that amount, right, as we increase the cycle time, the frequency goes down. Right, so if instead of 1 nanosecond, we had 2 nanosecond cycle time, we now have a 500 megahertz signal instead of a 1 gigahertz signal. So our clock cannot run as fast. And again, we can rewrite it in terms of propagation delay. TPD is less than or equal to, well, TC minus all this other stuff. But in terms of deriving the equation, this is the best way to derive it, and then bring T-skew over to the other side to see what we need, what equation we have for determining our cycle time. Now we can also consider the hold time constraint with skew. The worst case is that clock 2 is later than clock 1. So in this case, when clock 2 is later, well, we're considering the hold time off of the same edges, right? Instead of considering the two edges, one edge and it's the next edge, we're actually considering the same edge, right? What we call the leading edge of the clock. And so this leading edge of the clock, for clock 2, right, here's clock 2 clocking out the information, but now we're worried about the hold time of this clock. The whole time doesn't even start until a T-skew later now. So now our data that could be racing through and changing D2 before it's correctly sampled actually has a harder constraint because TC-CQ plus TCD has to be greater than not just T-hold, right? It still has to get to past that time, but now relative to clock 1's edge, it's driving this data T-skew plus T-hold. So TC-CQ plus TCD, that short path or that quick path through the circuit has to be greater than not just T-hold, but T-hold plus T-skew. So now we have a harder constraint to meet. And we can write it in terms of just our contamination delay again by bringing TC-CQ to the other side. And we get this equation that determines what is the minimum value of TCD, right? The contamination delay of this combinational logic has to be greater than T-hold plus T-skew minus TC-CQ. But again, deriving it, we would use this equation.